Let AB be rational, and AD equal AE plus ED. AE being greater than ED, be a first binomial. This means AE and ED are rational, but commensurable in square only, and their difference of squares is commensurable in length with AE, and AE and AB are commensurable. What we'll show is that the geometric mean of a rational and first binomial is binomial, or that if we make a square of area equal to AC, equaling AD times AB, its side would be binomial, the square root of AD times AB. Bisect ED at F and use proposition 10.17 to cut AE at G so that AG times GE is equal to EF squared. The same proposition says AG and GE are commensurable. Let's now make some rectangles by drawing GH, EK, and FL. Let the square SN equal AH, and the square NQ equal GK, and construct the rest of the parallelogram as so. Lemma 54 says SQ is a square. Now AG times GE is equal to EF squared, so AG to EF is proportional to EF to GE, and essentially multiply all of those by AB shows that AH to EL is proportional to EL to GK, so EL is the mean proportion between AH and GK. AH is equal to SN and GK equals NQ, and lemma 54 says MR is a mean proportion between SN and NQ, so MR is equal to EL, which will also equal PO. Overall, AH equals SN, GK equals NQ, and EL equals MR, which equals PO, which equals FC, because EF is equal to FD. So, AC equals SQ, and MO is the side of a square equal to a rational times a first binomial. We wish to show MO is binomial. AE is equal to AG plus GE. AG and GE are commensurable, so AE and AG plus GE is commensurable. AE is rational, so AG and GE are rational, and AH and GK are rational and commensurable. Thus SN and NQ are rational and commensurable. AE and ED are incommensurable. AE and AG is commensurable, and EF and ED are commensurable, EF being half of ED. So AG and EF are incommensurable, or that AH and EL are incommensurable, or that SN and MR are incommensurable. Sn to Mr is proportional to Pn to Nr, which is proportional to Mn to No, so Mn and No are incommensurable. Mn and No are also rational because they are the sides of rational square. Thus Mn and No are rational but commensurable in square only, so Mn plus No equaling Mo is binomial. Let's demonstrate this by taking the geometric mean of a rational and first binomial. The square root of 2, the rational, times 3 plus the square root of 5, the first binomial, is equal to the square root of 6 plus 2 root 5, which equals 1 plus root 5, a binomial.